Hello everyone, my name is Matthew Marcinko, and this is a summary of my project to determine at what speed of wind the Eiffel Tower will yield. This work was done for my final project for my Intro to the Finite Element Method course offered by Embry-Riddle Aeronautical University. So during this presentation, I'll talk about what exactly the problem is that I was attempting to solve for this project, my motivation for solving it, how I approached the problem to include some of the background research I did, how I ended up setting up my model, iterating through different versions of the model, how I actually got into executing the model, and then finally a summary of my results. So big picture, the Eiffel Tower was famously designed by Gustave Eiffel as a centerpiece for the 1889 World Fair. It was a tribute to the 100th anniversary of the French Revolution, and the Eiffel Tower was really an engineering marvel at the time. It was the tallest tower in the world, and it held that record until the year 1930 when the Chrysler Building was constructed in New York City. It's well documented by historians and engineers that Eiffel and his team didn't really use, obviously, the same numerical analysis methods that we use today. Instead, they used kind of a more primitive approach using structural engineering resources like tables, and they gathered experimental data to verify that their design would work. Obviously, after 138 years, we can confirm that the tower is structurally sound and is not at risk of falling. And it's really just a success. It's a beautiful and iconic work. A lot of work has been done by engineers and architects and mathematicians to look into this Eiffel Tower to not only verify that its structure is safe, but also just to kind of see the way that Eiffel and his team did construct the tower and kind of recreate it. So using the techniques learned in this class, Intro to the Finite Element Method, I'm now proposing my own version of an investigation to make my own claim on whether or not the tower is at risk of yielding plastically in high wind situations. Okay, so as I've covered, a lot of work has been done on the tower, mathematicians and engineers and scientists. Um, there's been modeling performed on the tower to not only determine if it's structurally sound, but also to kind of recreate it in a digital environment. Um, mathematicians have done work to determine like what mathematical equation, for example, was used to create the shape of the tower. And research has found that they used a exponential function, and we were able to find that the value of that function. While not explicitly used, obviously, in this um, project, I did utilize a lot of the work that other people have done in the past. So I'll kind of walk through the approach that I used and the process that I took to use past work to create my conclusions. So my first step was to build a model of the Eiffel Tower using actual geometry, material loading conditions. I then developed a global stiffness matrix. I created global displacements of each of my 60 nodes that I created for my tower, which resulted in a total 180 degrees of freedom. I then created element stiffness matrices using the displacements that I calculated that were associated with each element. Then I calculated axial, shear, and bending stresses associated with each element and used those to calculate the von Mises stresses in each element. Then I identified which one of those was a maximum value and compared that with the yield strength of the tower's material and basically increased the speed of the wind until a factor of safety was less than 1, which as we know occurs when a material will reach its plastic yield point, resulting in a material which will not return to its original condition after unloading. So that's basically the process that I used, and here's a visual representation of my version of the model of the Eiffel Tower. Obviously, it's not exactly the same as the real Eiffel Tower. It's a 2D simplification, which is essentially a 30 panel system. There are historical documents that indicate that Eiffel himself used a 29 panel system to model his tower. So I can't take any credit for incorporating this idea. So like I said, my model has 60 nodes. It has 117 elements, and I chose specifically frame elements uh, due to the ability to capture axial, shear, and bending responses of the system. I briefly considered using constant strain triangular or CST elements, but I quickly scratched that idea. I think I only picked that because it would have been convenient uh, based on the geometry of my elements and just based on the natural triangular shape that they took. But my experience was kind of showed through because I would have mistakenly modeled what should have been what could have been modeled incorrectly as a plate instead of using a lattice joint structure like it really is. So I'm glad I didn't see that work through. Okay, so in general, I wanted to create like I said, a digital representation of the Eiffel Tower, and so that required me to kind of make a matrix of um, all of the properties and all the dimensions of the tower. So using the coordinates from past research and the material properties determined by others, I'd use some trigonometry to basically create an inventory of all the dimensions and properties of the system. My first task, as shown on this slide, was to identify the angle between what we call the local axis of each element and the global axis, which you can see kind of in the middle there is the positive x-axis points to the right. And so my task was to create basically an angle between those two vectors for each element. Fortunately, all of them were some sort of version of the six um, iterations you see on the slide here. So it was fairly easy once I solved it once to basically apply it to the rest of the elements. So to deal with what I'll call my configuration management of this process, I ended up using Microsoft Excel to create what was a basically giant spreadsheet of all 117 elements and all of the nomenclature and the dimensions and the properties associated with each element. So I'll walk through basically each of these columns. And again, I made this for all 117 elements. So there's two nodes associated with each element. So I made sure to keep a pretty disciplined track of which nodes were with which element. Some of the elements were associated with a handful of nodes. Some of them were only associated with two. So I had to make sure I could keep good track of when I was making my displacement matrices, which ones should be in the correct order. I use the coordinates outlined in previous engineering work in the digital environment to basically calculate using trigonometry the horizontal length and the vertical length of each element. Then I use Pythagorean theorem to calculate the actual length of each element. I use the process outlined in the previous slide to determine the angle theta, which is the angle between the local x-axis and the global x-axis for each of the elements. I then calculated the sines and cosine values corresponding with the frame global stiffness matrices for a frame element. Then again, I used research from previous work to identify the dimensions of the area for each element, identify the area moment of inertia for each element, and then the material properties like Young's modulus. I then calculated the volume for each element using the length and the area, and use the density of the material to calculate the weight of each element. So here's the stiffness matrix that I developed for a frame element. Again, I used the data from my spreadsheet and calculated this for all 117 elements. Some unique methods that I used in pursuit of this investigation included, like I said, the node numbering was a little irregular. So I made a connectivity matrix that basically identified which nodes were connected in order for each element, which I then used that when I calculated things like displacements and when I made the force vector to make sure I had the order of which displacements were associated with which nodes. I made sure those were in the correct order. In general, a lot of the difficulty in this problem was dealing with such a large system. So having good configuration management was definitely helpful. Okay, so for my force vector, I consider two sources of load. I consider the self weight of the tower, which was determined by some research that I had done on the current weight of the structure. Um, then I used that as kind of a check in my mind, a sanity check to make sure what I used by calculating the density or by calculating the volume multiplied by the density to calculate the weight of each element was kind of a logical answer. Um, it turns out that my model is about 25% of the total weight of the real Eiffel Tower, which makes sense when you consider this is just one 2D side of what's a four-sided structure. So I was happy with having that verification. I then apply the weight of each element as a downward force on each of the 60 nodes, which is basically calculated again based off the individual size of each element. Um, then I also had a wind force, which was the most important, obviously, for this specific study. I applied a approximately 12 mile per hour wind to the structure, which I converted basically into a pressure and multiplied by basically the width of the structure to determine an actual force for each element. I use what's known as tributary height, which is essentially just accounts for how much of the total weight pressure is being influenced by a particular length of an element. I use that to determine what the force was for each individual element to account for the total magnitude of the wind. So here's an example of what my code looks like. Again, I use the connectivity matrix on the force vector here, and I associated all from 1 to 117 elements with the appropriate X and Y loads. So once I had the force vector made, I was able to calculate a displacement vector, which I kind of used as a sanity check when I was doing my troubleshooting of the model. But once I was happy with the displacements, I then moved on to calculating the element forces for each element. So I created a local element stiffness matrix as well as a transformation matrix that I then used to calculate the forces associated with each element. So at this point, I had 117 6/1 matrices, which I was then able to use to calculate the axial bending and shear stresses for each element, which then created a corresponding von Mises stress, which I was able to pull the maximum value from all of the system to compare to a yield stress of 190 megapascals and calculate a factor of safety. I think it's worth mentioning kind of the issues that I ran into during this project. At first, I ran into several issues where I had unreasonable values that were corresponding to basically inappropriate results that, in my mind, didn't make any sense. For example, I had a 12-meter displacement in like an 11.6 mile per hour wind, which intuitively I just knew didn't make any sense. So it turned out that I had just forgotten to include something in my code, which I'll talk about in the next slide. So I basically troubleshooted all of these issues until I had a reasonable result. And again, much of the challenge for this project was just managing the transfer of information between my brain, Microsoft Excel, and MATLAB. So again, some of the mistakes that I made, which I caught in my code, were I forgot, or at one point I decided I was just going to run the model as is and then apply boundary conditions at the end. Turns out the code did not work until I had done my boundary conditions. So once I resolved that issue, the errors went away. I also forgot to divide by the coefficient in the global stiffness matrices. So I didn't divide by the element stiffness matrix, which was a huge number. And so I was getting really big displacements. And that's why I had that 12-meter displacement in the like 12 mile per hour wind. Okay, so finally, the moment we've been waiting for. What is the answer to our question? At what wind speed will the Eiffel Tower yield? So using the extensive analysis outlined in this presentation, I concluded that the highest element stressed was element number 2, and that was the limiting factor. And I'm proud to state that after all of the work I've done in this project, I can conclude that at a wind speed of 183 miles per hour, my model of the Eiffel Tower will experience its first plastic deformation. So first, I just want to state that this project was certainly no walk in the park. It was a major challenge that I'm really proud that I was able to overcome. Just a sanity check, the wind speed of 183 miles an hour is about 16 times higher than the windiest recorded times in Paris. Considering that my model is basically a 25% scale of the structure, I'm fairly happy with it. Future work could involve more analysis, three-dimensional analysis. And in general, when you go to Paris, you should feel safe going up the Eiffel Tower. Thank you.